Okay, so in this video, we're going to talk about functions or mappings. Some branches of mathematics distinguish the two, but we won't be doing that. Let's go over the definition. We're going to need a relation. So let f be a relation from A to B. Now we say that f is a function. And again, it is a function from A to B if it is subject to the following condition. Now this condition right here is going to be extremely important, and that is for all elements x that is in y, that is in A, there exists a unique y that is in B, such that x is related to y by f in this order. Okay, so some keywords here. For all elements x that is in A, there exists, and it is unique. So there exists a unique y in B such that we have that x is related to y by f. So we're going to need to do some talking here. Very important that you understand what this condition means, that you fully understand it. So let's start with two potatoes, two Venn diagrams. This is going to be my function f. This is my set A. This is my set B. So let's have some elements inside. Let's say 1, 2, 3, 4. And here let's have 1, 2, 3, 4, and 5 right here. Let me write that a little bit clearer. So 4. Okay, so the condition for all says that every element that is in A has to be related to a unique element that is in B. Okay, which means that 1, 2, 3, 4 has to be related to an element in B. Now, what the unique part means, I can't have 1 to be related to 5 as well. I'm simply not allowed to have that because 1 has to be uniquely related to an element of B. Now notice that I don't have any for all quantifier for my elements in my set B, which means that this element 5, okay, the 5 that is in B, I don't need to have any element in A to be related to 5 in B. This isn't a requirement. Now this definition is the reason why in high school, when we defined what a function was, we had the y-axis here, we had the x-axis, and we have a certain curve like that. We're not allowed to have every element in the x-axis has to be uniquely related to an element in y. But we're not allowed to have two points on the same vertical line. And that comes from this definition right here. If we had 2 points on the same vertical line, this would mean that for one element x, let's say 3 here, it would be related to 2 distinct elements. So this is something that we want to avoid when we're talking about functions, at least. Now we're going to add some terminology. We're going to say that A is the domain of f. B is the codomain of f. Now x is a preimage. It is a preimage of y, and I say a preimage because I can have, let's say I would want an element 5 that is in A. I could have 5 to be also related to 4. So the element 4 that is in B would have 2 preimages in A, which are 4 and 5. And y is the image because it is unique, the image of X. The image of 5 in A would be 4 in B. Now, when we're talking about Cartesian products, we say that X, the pair X and Y, are elements of the product A and B. When we're talking about relations, we say that X is related to Y by F in this manner. But when we're going to talk about functions, we're going to adopt the usual notation, which is, you're probably familiar with that, f of x is equal to y. We can define functions this following way. We can say that f goes from A to B, and the action, the way I'm associating the elements with a vertical line at the start of the arrow, sends x to f of x. And I can say that f of x, the image of my arbitrary element, I can say where I'm sending it to. When the action isn't very important, sometimes we're going to opt to write f is a function from A to B in this way. And this will allow us to talk about diagrams. If I have another set C, I can have another function G and H. You can have some diagrams like that. And sometimes all you need is to talk about from which set and to which set your function is defined on. Now, I think some examples are long overdue. The simplest function is the identity function. So we're going to say it's the identity function on A, and it is defined by the function that goes from A to A and sends every element x that is in A to itself. So this is the identity function on A. And this is a very important function, especially when we're talking about invertible functions. So this is our first example. We could have also the function f. I could define it to be on the sets, using sets of real numbers, and say that it sends x to its square. This would be your famous parabola function, like this. Now, what you're not allowed to do is send x squared to x, because now what it would look like in a graph would be this right here. Because in this case, I would be sending 1 to 1 and minus 1, okay? So this here, you're not allowed to define such a function, okay? It is not a well-defined function, we say. I could define another function, not f. I could define the function g to be the product of two sets of real numbers to one set of real numbers. So I could send the pair xy to simply x, okay? And this would be what we call the projection of the plane onto the x-axis. And this means that we take all of the elements, let's say on this line, and we send them to one point on the x-axis. Okay, so all of these points would be mapped to the x-axis. Okay, and all of the points on a vertical line would be sent to the same point on the x-axis. So this would be the projection of the plane R2 onto the x-axis. Then we could talk about, the canonical injection, okay, which is defined, for instance, by I, the function I, with two sets, so e to f, for instance, and we're going to say that e is included in f, and we're simply going to send x to itself. So this is the canonical inclusion or injection. I'm going to write injection. I think it's cooler. From E to F. and that simply takes the set E and it sends it to the set F, where E is a smaller part. It is a part of F. I could spend like hours and hours giving you examples of this, but functions are ubiquitous in mathematics. So as we go on in other videos, you're going to see more examples. You're quickly going to be comfortable with this. So let's go over an overview. We have f is a relation from a to b, and f is a function from a to b if it is subject to the following condition. Very important. For all elements x that is in a, there exists a unique y that is in b such that x is related to y by f. I really want you to memorize it, internalize it, this condition right here. Remember, you can make a mental image of this condition using potatoes or Venn diagrams, if you want to call them that way. A is the domain of f, b is the codomain of f, x is the preimage of y, and y is the image of x. So the elements in A are preimages, and some elements of B are images. So we're going to use this notation right here for functions. And the way we're usually going to be defining our functions is this way right here. We're going to say that it goes from A to B and it sends our action, sends x to f of x. And sometimes we can choose to draw some diagrams of functions. As for our examples, we've seen the identity. We've sent x to x squared. And remember, you're not allowed to send something like x squared to x because it would lead you to have multiple points on the vertical line. So for one element in the domain, we would have two images, and we're not allowed to have that. We talked about the projection of the plane onto the x-axis, and we talked about the canonical injection, which simply injects a set into a larger set.